This is a presentation from our head of the PHiL department that was done in RT24. So if you were there, you might have seen this. But this is the idea of, we just took that basic idea and now let's apply where Cinergia comes in. So you guys know the analog interfaces with Cinergia. So we output analog signals that correspond to set voltages. The Cinergia is then going to turn that into the power signal that we're actually going to use. So over the last while, we've seen hardware in the loop really develop because computationally, we're finally at a point where we can solve these numerical ODEs fast enough to be in real time. That only really became possible in like the late 90s when OPAL-RT and a few other HIL companies showed up. And we've seen it grow as it becomes cheaper. There's more diversity in the business and more engineers understand how to use it. And along that same trend, we've also seen a lot of growth in PHiL. So we've started to see people start to get their masters and PhDs in PHiL and other applications. Sebastian, who made this presentation, did his doctorate in it, and he's our expert in Europe for PHiL applications. So he's my trainer and he's my technical resource on this subject. So this is the presentation. I'm not going to go through this whole thing because it's like an hour-and-a-half presentation. I'm going to give the highlights, but you'll get all the slides and you can go through it. There's papers and references at the end. So if you're really curious, there's further reading for you to go through. But the basic idea in test environments is we have our test environments, and then we have the component we want to test. With like the Cinergia line, for instance, when you're testing the Cinergia, that's the component under test. And the test infrastructure is like the analog signals you're sending in. You're not testing those analog signals. You know how they operate. You're confirming that the system is going to work like you expect. So that's like end of the line testing standard things we should all be aware of. With hardware in the loop, we replace this known component with a simulated component. So instead of having a power supply or another device, we do it all via the CPU and the SFPs and all that stuff. So we simulate a physical system instead of having a real physical system. And then we send digital and analog signals or SFP signals or data out somehow. We read data back in, and then it gets simulated and we run our tests. So that's what we just saw. This is HIL. PHiL is when we're not just doing basic command or control signals, we're doing high power signals. So this power amplifier and this transducer section is the Cinergia. We at Opal manage all of this. So we handle the simulated test environment, we handle all of that physics, and then we send out an analog signal that goes into the Cinergia. And we usually use it in power amplifier mode. So we're actually sending out instantaneous values every 25 microseconds, every 10 microseconds, which is setting the curve. So we can have really sharp commands over faults and other things. Whereas if you're in RMS mode, you're limited to the level of, how quickly the system can respond. So we send that data out. The amplifier itself then generates the output that actually goes to the physical hardware. So I know Cinergia uses their systems for like end of the line testing or R&D. So that would be the same idea. Like wherever you would use a Cinergia, you can do the same thing here. The value add or the reason you would bring the Opal in is you want to go beyond the grid emulation mode or like the battery emulation mode or those built-in features. You want dynamics that are much higher. You want a very custom system, or like we'll see, you want to simulate a large grid that's very precise. So it lets you take kind of a larger angle and then use the Cinergia to connect. So in cases where the Cinergia built-in grid emulation, electronic load emulation, PV or battery emulation, when those things work, there's no reason to use the simulator. It's just extra hassle. What we look at is when those aren't enough. So when you want to see dynamics beyond that, what's capable in the Cinergia, we can command it via the analogs, and then we basically have this high-speed real-time controller to manage those kinds of signals. So some ideas of what you've done or what we've seen is like power grids. So rather than having it be an idealized grid or just a grid with harmonics, we can have like a distribution system or a transmission system. So we can see like vibrations or oscillations in the line. We can see transmission delays. We can see faults on the line. So you can simulate all of these known phenomenon that are more challenging to do directly in the Cinergia. And then the real hardware are things that you've probably already seen before, like batteries, loads, inverters, machines, anything that takes DC, AC, whatever it might be. I'm not going to teach you guys about Cinergia. You guys know it better than me. We also go the other way. So you can also use the Cinergia as a power grid, and you could watch how, for instance, people use like AI monitoring or other advanced monitoring. So if you inject harmonics from the Cinergia, it can detect it and try to respond to that. We also do things like cybersecurity. So you might want to simulate what happens if there's a cyber attack. That's not something you can do in Cinergia. So you can simulate a cyber attack here, and you can see how your power equipment is going to respond to that kind of event. We work with another company called Exata. So I'm also a cybersecurity expert. So we look at how does power hardware respond if it's attacked. Things like how do you build controllers that even if one of them is compromised, the rest go into isolation mode and protect themselves. So that was in response to, for instance, the Ukrainian attacks that happened. In 2016, Russia attacked Ukraine's power grid and shut it down for a couple of days because they were able to get root access to the electrical grid. So people are studying how do we prevent that from happening, and if someone gets in, how do we minimize the damage and fix it as quickly as possible? And you can do all of that together in one big simulation. So yeah, some perks. You can be more varied. It's quite secure. You can reproduce exactly your results. And it's also a lot cheaper to do, again, because if you want to test how does my controller or my device respond to a current spike or a voltage spike, you can replicate the exact same test over and over, and you don't have to damage anything to do it, because you can use your Cinergia to simulate a voltage spike or a current spike if you wanted to test a fault response, for instance. So yeah, so overall kind of objectives, you can look at all of the system dynamics. So you have a much wider net you can cast. You can have detailed models of all the components that are present. And it is a stable test environment. We use the term quasi-continuous because it's discretized. So again, you have to be careful about, am I losing out on a phenomenon that's present? So instead of having this real system, that has an actual source, this is like the circuit representation. So we're actually using this as a voltage source or a current source. You have some simulated impedance on this side, and then on the real side, you can have a real device that might be present. With Cinergias, you can also put them back to back. So you can have one operate as a simulated load, one operate as a simulated source. You can also do that here. Or you could do that with like an inverter in the middle. So one Cinergia giving your DC inputs, then the inverter gives out your AC, and that goes into another Cinergia. So instead of having to test that and like expend money on electricity, because it's all going in a circle, you don't lose any money. The problem and the challenge with PHiL is what's called stability or numerical stability. Because you're sending it through so many steps, you end up basically you have to trade off between three factors. How detailed your model is, the dynamics and bandwidth that you want to operate with, and then how stable is that system to disturbances before numerical instability sets in. We'll see in a second what I mean by that. It'll be a little bit of math. We'll get through it quick though. But this is the trade-off. Because Cinergia has a fairly low bandwidth, it's only about 400 hertz, generally simulations are very stable with Cinergia because the bandwidth is not as high. It's really when you start to get into higher bandwidth simulations or you start to get into very rapid dynamics when this really begins to set in.